If I was bad, his math sense would be like, okay. Be like, oh, somebody's saying something wrong.
Figure out how to talk like that.
Alright guys, let's do this. I'm going to do the first one. I'm going to give you a few more minutes to do the second one. And of course, anytime you want to, this is nothing you got to turn in. If you'd rather work on quiz corrections or whatever else, you totally can. So, let's do this. Let's do part B first, and then we'll come back and see if you guys can get part A. Some of you guys already did. If you already got it, just kind of be happy about it and sit on it. So if I assume this is normal, right, so I'm telling you to do it, don't worry about why you can't, just do it. Find the probability that this woman that we pick will have a bone density more than 2.5 grams per square centimeter. So you don't have to understand any of the underlying biology or whatever. You just draw your little picture. You know, we're assuming it's normal, so I can draw this. What goes right in the middle?
Mean.
Yeah, and remember, average is another name for mean. So 2.9. And then I'm curious about 2.5. So I want to put the mean on there, and I want to put all the data points that I'm curious about. I'm just curious about one data point, 2.5. Where's that?
Left.
Yes, please, dear God.
Okay.
And then I want to shade where?
Right.
I want to shade more than. So now, and I like that somebody actually did this, because I'm never sure if anybody likes or understands what I mean by this, but I've been given raw scores. I want to convert them into z-scores so that I can use the z-score chart to get the probability. Right? Maybe. So that's the kind of outline. That's the overarching outline of a normal, traditional, classic z-score problem. So what do I still have to do? I haven't actually done any of that yet. So I got to change this using z-score formula, which is, I like it. So x minus the mean divided by the standard
What's
deviation.
that weird R called again?
It's not an R. It's a fat R. It's an R that's had a good life. It's a lowercase sigma.
Oh, lowercase sigma.
Yeah.
Yes, okay.
It's all right. This is not a Greek class. I'm not gonna. If you make it an R, it's bad because we actually have an R coming up later this semester that means something else entirely. So you want to make it a fat. Now watch, real quick, just to show you. Start at the belly and go out like that. If you try to go in, it always gets weird. It's like a sickly 6, right? But you start at the belly and go out to the nose. It's a weird creature, and all it is belly and nose. All right. Yeah, I'm the last person to give you anything about art, but I can make mathematical variable symbols.
2.5
Good. My data point.
minus 2.9 over 0.7 squared.
Negative 0.56.
Yeah, so negative 0.56, that sounds right. So this is negative 0.56. If I wanted to, this would become 0, right? So I really want you guys to understand, when you say 0 goes in the middle, it's partially right. If it's converted to a z-score, it will be 0, but you put what it actually is first. If it's a z-score problem, then it is 0. There are already z-scores, and you would put 0 in the middle, like on that handout. But the second part, we didn't put 0 in the middle, because it was however many minutes it was to find a parking spot on that problem.
Yeah.
So now, this is a z-score. I can look it up. Does anybody need a z-score chart? You're all good? Don't forget, you got to bring this tomorrow. I might have a couple spares. No problem. So if I look at negative 0.56, negative 0.5... I'm not laughing at you, just laughing near you. Negative 0.56 looks to be there, right? 0.2877. Where is that on the picture? Good. Every time you look up a z-score, it shows the area to its left, below it. So that's 0.2877. So how do I get the actual answer?
1 minus that.
Yeah, 1 minus 0.2877 is 0.7123. Yes, ma'am.
How can we write it so that, because I just did positive 0.56, but how can we write it so that you will
all right, so if you
accept
do the shortcut, do this, the little arrow,
it? Okay.
0.56, and then you can go straight to the answer. That's fine.
Okay.
And that'll tell me that you're using the shortcut.
Okay.
If you don't like the shortcut, it doesn't really save you a ton of time. It shaves off a few seconds.
No, I'll give you a second share.
Okay. So what happens? All right, so let's go back to part A. What part of what we just did could I not have done if it wasn't normal? No, I could have done all the way to here. You can get a z-score for any distribution. You can get a z-score. It just tells you the number of standard deviations away from the middle. It has nothing to do with it being normal, or it doesn't matter. I can just get a z-score anytime I want to. But the next step, how did we get this number? We used this, and this only works if it's normal. It's got a little picture on it. So the very first part, why must we assume this is normal? Because we want to use the z-score chart, and it only can be used when it's normal. Don't say because it didn't tell me. Well, yes, I didn't tell you, but why must we know it's normal? Right? Why is it important? Why must we assume it's normal? So I can use the z-score chart.
But what if it's not normal and we just can't use the z-score chart?
Then you say, I can't do this problem, and keep going. To be on the safe side, you should say, I don't think I could really do this because I don't think it's normal, but I'm going to do it anyway in case you miss something. Because I'm not going to do that to you. I'm not going to give you a problem that's all this stuff. And if you just don't notice it's not normal, you're wasting all this time. And I'm back here going, that's right. You know, maybe 10 years from now, I'm like, screw all you kids. Me just make it. Hey. I'm not quite there yet. Some of you guys think I am, but I'm not.
So we just say that you can use a z-score chart if that's the answer?
It's in order for us to be able to use the z-score chart. If it wasn't normal, I could never look up the probability. I could never finish the problem. Yeah. All right. So here, why do we not? I'll just tell you, the answer to this question is no. We don't need to assume. Why do I not need to assume?
Because the sample's over 30.
Yes. N is greater than 30. What kicks in then? Probably the title of this thing. The central limit theorem. The chicken, lettuce, tomato theorem. I like it. A nice BLT, but with chicken instead. All right. Sorry. Takes me back to the MLT. Mutton, lettuce, tomato. What's got to change here? So notice how this is a little strange. It's almost the exact same question I asked up here, right? This question is almost the same, except I took a sample, and I'm asking about the sample mean. So what's got to change? Beautiful. Because this standard deviation works for what? Individuals. So that's why it was perfect for this problem if we randomly select a woman. So that is an individual person. That is how spread out individual women are. Now I'm talking about a group of 38 women. I have to know how spread out a group of 38, all groups of 38 women are. That's what I get when I do this. So I got to change the standard deviation first, and then everything's the same. So the old one was 0.71 divided by the square root of n, which is 38. And what do you guys get for that?
1.115.
1 and 5? Okay, cool. So at least 3 places in that. You can go more if you want to. Maybe not 12 or something crazy. So here, the work is going to be exactly the same because it's really almost the same question. It's just talking about the mean now. So it's going to be 2.5 minus 2.9 divided by the new standard deviation. So it's the same picture. You can make it skinnier if you want to, but it's the same idea. I want to know this area. So I got to change 2.5 to a z-score, but now what's changed is the standard deviation is 0.115, not 0.71 like it used to be for individuals. Can you guys see? I don't like to. It took a long time for me to explain why this is true. I desperately hope you got something out of that. But at the very least, I hate to teach it this way, but the trigger is if I take a sample and I ask about the sample mean, you know you must change the standard deviation. The one for individuals won't work anymore. So what do you get when you do this here?
Negative 3.4782.
So 348?
Yeah.
Cool. So always truly round it to 2 places. Why 2? Because the chart only goes to 2 places. And when we look at negative 3.48, 0003, I like it. And that's, of course, down here. So our answer is going to be 0.9997. So put it up here just to make, so like almost 100% chance. Why does that make sense? Because originally, so real quick guys, originally it looked like that. When I take samples of size 38, the new picture looks like this. So now how much is above 2.5 in the second picture? Almost all of it. It's all rushed to the middle. So above 2.5, it's going to be almost all of it's in there now. Whereas they used to have a much bigger tail back here. Right? Don't talk about that. It's a little sensitive about that. But there used to be a lot more below 2.5. That's why there wasn't as much above it. But now almost all of it's above it. It's all rushed to the middle. Do you have to understand that to answer that question? No, you don't. All right. So very quickly, let's. Just realizing what time it is. Let's finish this out real quick. This next part, I just wanted to do another follow-up just to have a different setup, but it's the same exact problem, right? I just asked a few more questions. The first two, both of these are classic z-score. Nothing's changed. It's just, I'm picking one person, so nothing's changed. So how would I draw this picture? What would be in the middle?
79.7.
79.7, yep. And we know it's normal, so I know I can do that. And where's 79? It's a little bit below it, but I'm just going to over-exaggerate, so I got somewhere. And I wanted it probably is less than that. So you do enough of this, and you start to get the feel of it, the flow. I draw the picture, I find the data points that I'm interested in, I make them into z-scores, and then I look it up in the chart. Right? So if I change this to a z-score, it'll be, what goes on top?
79 minus.
Good. My data point minus the mean. And the standard deviation here is 7.6. And this was actually true when I looked it up a couple years ago, I think. I found a website that had some of this stuff. Anyway. Yeah, there's Z. So what do you get when you plug this in the coupler?
Negative 0.092.
So 0.09? Negative?
Yes.
That's negative 0.09. So when you look up that z-score, the really beautiful thing is, that's the answer, because I want below that. So when I look at negative 0.09, negative 0.09, I get 0.4641. How are we doing? Is that right? So it's 0.4641. Bam. That was horrible, Jeff. Oh, stop it. 0.4641. Bam. So part B, the only difference in part B is you have to find both z-scores, find their areas, and then subtract them, right? So I just got two z-scores to create. So 62 minus 79.7 over 7.6. 71 minus and then whatever they are. That was neat. It's very delicate, whatever you just spelled. I don't know if you guys got here yet, but we did quite a few of these types where you look up two areas and you subtract them. Right? Did anybody get the z-score for 62?
Negative 2.22.
2.20? It sounds familiar. And this was negative 1.10?
2.33.
Just 2.33?
Yeah.
Well, let's see. We got dissension in the ranks. So let's see.
Yeah, that's right.
What's right?
Yeah.
What's right?
2.33.
233?
Yeah.
We all agree? Okay. I'll take your word for it. 233. And this is negative
1.14.
114. And then you just look up there now. So my picture is going to be 79.7 in the middle. There's 62. There's 71. I want to get that area, so I find the two areas and subtract them. I'm kind of picking up speed here, but that's because we're running out of time. So if I look up negative 233, I get an area of, what do you guys get? 0099, I like it. And if you look up negative 114, 1271. And if I subtract those, I'll get that area. 0.0. Yeah, 0.1172. All right. So about 11, almost a 12% chance somebody born in Florida now would live to be somewhere between 62 and 71 years old. That's physically what that answer means.
All the data that you give us is true?
This was true a few years ago when I looked it up. It might have changed by now, I would think. All right. And then finally, what changes on this part? Yeah, you just change the standard deviation from what it was to divided by square root of 87, because the sample size is 87, and whatever that is. And then you just redo this z-score, but instead of 7.6, you're going to have the new standard deviation there. So whatever that is, I don't know. What is 7.6 divided by square root of 87? 815?
Yeah.
And then your z-score formula looks the same. 815, and then you get
Negative
0.86. And then I looked it up just to complete this. 0.86. 1949. Good old 1949. Alright, so I think that was even more helpful than I thought it might be. You guys desperately, this kind of question should be relatively easy. It's just knowing when to change things that gets more weird. Oh, you probably want the answer key, right?
Wow, I actually have that. I didn't even try to do that.